In mathematics, specifically in the representation theory of groups on algebras, an irreducible representation or irrep of an algebraic structure is a non-zero representation that has no proper subrepresentation closed under the action of every finite-dimensional unitary representation on a Hermitian vector space is the direct sum of irreducible representations. As irreducible representations are always undecomposable, these terms are often confused. However, in general there are many reducible but indecomposable representations, such as the two-dimensional representation of the real numbers acting by upper triangular unipotent matrices. History. Group representation theory was generalized by Richard Brouwer from the 1940s to give modular representation theory, in which the matrix operators act over a field of arbitrary characteristic, rather than a vector of real or complex numbers. The structure analogous to an irreducible representation in the resulting theory is a simple module. Overview. Let be a representation, i.e., a homomorphism of a group whereas a vector space over a field, if we pick a basis for, can be thought of as a function from a group into a set of invertible matrices, and in this context is called a matrix representation. However, it simplifies things greatly if we think of the space without a basis. A linear subspace is called invariant if for all and all. The restriction of to a invariant subspace is known as a subrepresentation. A representation is said to be irreducible if it has only trivial subrepresentations. If there is a proper non-trivial invariant subspace, is said to be reducible. Notation and terminology of group representations. Group elements can be represented by matrices. Although the term represented has a specific and precise meaning in this context, a representation of a group is a mapping from the group elements to the general linear group of matrices. As notation, let A, B, C denote elements of a group G with group products signified without any symbol. So AB is the group product of A and B and is also an element of G. And let representations be indicated by D. The representation of A is written by definition of group representations. The representation of a group product is translated into matrix multiplication of the representations. If E is the identity element of the group, then D is an identity matrix, or identically a block matrix of identity matrices, since we must have and similarly for all other group elements. Decomposable and indecomposable representations. A representation is decomposable if a similar matrix P can be found for the similarity transformation, which diagonalizes every matrix in the representation into the same pattern of diagonal blocks, each of the blocks a representation of the group, independent of each other. The representations D and P-1 dP are said to be equivalent representations. The representation can be decomposed into a direct sum of K matrices. So D is decomposable, and it is customary to label the decomposed matrices by a superscript in brackets, as in D for n equals 1, 2, K, although some authors just write the numerical label without brackets. The dimension of D is the sum of the dimensions of the blocks. If this is not possible, then the representation is indecomposable. Applications in theoretical physics and chemistry. In quantum physics and quantum chemistry, each set of degenerate eigenstates of the Hamiltonian operator makes up a representation of the symmetry group of the Hamiltonian, that barring accidental degeneracies will correspond to an irreducible representation. Identifying the irreducible representations therefore allows one to label the states, predict how they will split under perturbations, and predict non-zero transition elements. In quantum mechanics, irreducible representations of the symmetry group of the system label the energy levels of the system, allowing the selection rules to be determined. Lie groups. Lorentz group. The irreps of D and D, where J is the generator of rotations and K the generator of boosts, can be used to build to spin representations of the Lorentz group, because they are related to the spin matrices of quantum mechanics. This allows them to derive relativistic wave equations.